but he is also a leading expert in the world. You will be receiving your classes from a leading expert in the world on observational astronomy and instrumentation. Professor Leopold, as you can see in the short CV in the web page, has worked on several very well-known projects. For example, as ESA Hipparcos, which is a very well-known satellite, as you know, but also in projects like the BLTI and other projects, other observational projects in the world. So, as I told you, Professor Rudolph, I expect that you take the best from Professor Rudolph and enjoy his classes. Professor Rudolph, thank you very much for being with us. And also, you enjoy this week. Let me.
Yeah. You, Professor Zuluaga, for the...
Yeah, no, let me.
Yeah, I will come.
While the computer is on. Información pequeña, entonces, lo mismo. Tenemos las mismas clases de 1 a 2 y media y de 4 a 5 y media. Except on Friday. On Friday we will not have the second session, but we will have public lecture in the planetarium at 6:30. I strongly recommend to go to the public lecture because you will enjoy to see, first because it's in another topic, which is astrometry. And the second thing is that you will enjoy seeing your professor talking to a big audience instead of doing academic lecture. You will enjoy. We enjoyed the Kuhn lecture last week. Lo mismo, tenemos una tarea por día. La tarea no hay que entregarla, sino que la tarea es el material para preparar el examen del otro día. Vamos a tener otra vez 4 exámenes. Ya saben ustedes la dinámica. Los que están viendo cursos de astronomía, otra vez, pídanle a sus profesores que les incluyan algunas de las actividades del curso como parte de los cursos, ¿ok? Para que todo vaya bien. Pregunten mucho, aprovechen para que tienen aquí al profesor Rudolph y probablemente no lo van a tener después. Ok.
Thank you very much, Professor Zuluaga. Thank you all for being here, and I find it extremely exciting to come and have this opportunity in this fascinating university to talk to these eager young students that are going to take our job further than we could carry it, because at some point we can't quite do it anymore. For the time being, I still try hard. In order to make this a success, we have a few handicaps. Like, one is I don't speak your language, and I speak another language. And that is a handicap for you more than for me, because this language is relatively easy for me. If it is too easy and you find that I'm talking too fast, please let me know. So if I'm not understandable because I go too fast or because of whatever other reason, please ask straight away. Please, can you tell it another time? Or why do you think that is right? Or something like that. Make sure that you do not miss what I'm trying to tell you by asking the proper question. That way we can team up and make sure that it works. Otherwise, we have a hard time. I have this extra handicap that Professor Kuijken did not have. He is sufficiently good at Spanish that if you ask a question, he could answer that, although better in English again. I cannot answer a question posed in Spanish, unfortunately. I wish I could, but I just don't have that available. So please let me know whenever you think I'm not sufficiently understandable.
But if you have a question in Spanish, we can try to figure out how to. But don't. Yes.
It's better to find someone next to you who can translate your language, your Spanish question, and still pose it so that the question reaches me in English. There's sufficient people around who can do that. So please make sure that if you have a question, that it does get answered. That's what I'm here for. There's another problem that I have. I'm not particularly good at sticking all these very beautiful slides together. So I have almost disgracefully borrowed from lots of very good colleagues with whom I have worked in the area very often, and without whom I could not have done what I have done in this area. So I just let you know that I'm extremely happy with the contributions of all these colleagues, many of whose names you will find in the course of the event. And then let's just start off with asking ourselves the question what we are supposed to be here. We are going to look into interferometry, and interferometry is a very special sort of technique. Basically, it's doing something difficult what can be done very much easier. At least that's the way we have learned to do it. What we have learned to do is we make a nice big hollow telescope that focuses the light and brings it all to one point, and then you put your sensor in there, and there with you can look in a specified direction and very precisely and very carefully. And why is that not enough? Okay. So why is that not good enough? Well, that's very easy. Our eyes can look relatively precisely. If you do the calculation, we can see something that should even be better than an arc minute. I don't think there's very many people that have eyes that are that good, but you can see of the order of slightly bigger than an arc minute. It's the finest spot you can see. So two things separate from one another are at least an arc minute apart. But an arc minute, with the wavelength of regular light on the pupil of our eyes, is half a micron, half 1/1000th of a millimeter in 5 millimeters. So that's about 1 part in 10,000. That's why I was saying you could do even better than what you're in fact doing because of the imperfections in the human eye. And therefore you can only see an arc minute. You could even do something like half an arc minute. But the radio telescope, where the wavelength is not half a micron, 1/2000th of a millimeter, but is 2,000 microns, even much more, 20,000 or 200,000 microns, like 20 centimeters, then you cannot look at 1 arc minute anymore. In that case, you would need a telescope which would be about 4,000 times the wavelength in diameter. And we can't make those. So it's very easy. What we want to do, you cannot do by making this very big telescope and then be sufficiently precise. And in fact, this story goes much further. We want to look not just as good as the human eye, but we want to look as good as an optical telescope. And in fact, we want to look even much better, because also optical telescopes have their limitations in sharpness, and we want to try and do better. So all the tricks that we can master to look sharper and sharper are the tricks that we need to do, and that is, I hope to convince you pretty soon, is all about comparing light that arrives on one side of the aperture, whether that's the true aperture or an imaginary aperture is not particularly relevant. The light that arrives here, I want to compare it to the light that arrives there. And in comparing it, I can see the direction from which it arrives more precisely than when I can compare it very close together. That's the whole trick of interferometry. Now, you all know interferometry from the early experiments by Young, who demonstrated that light is an interference, it gives an interference pattern. So I make from a sun, which is very big, it's a full half a degree, I make a point source by having a tiny little spot, and then some distance away I illuminate 2 little spots. These are colossally big, so you get all sorts of troubles by having them that big. But then from here on, again by Huygens principle, you see the light coming out, and then it meets light from the other hole, and it constructively or destructively interferes, depending on whether the waves are going in phase or they go in counter phase, and that happens depending on, that basically just depends on one thing, that's the path length difference. So, in fact, there's more to this in terms of physics. you can see that the intensity of the wiggles gets less when you go further away. And that has to do with the fact that we're not only looking at red light, but we're also looking at yellow light, or we're looking at much different colors. And so if it is in phase in the central wavelength, then in wavelengths which are a bit shorter or a bit longer, it's already beyond phase or before phase. And so you do not get as much coherency as you would have otherwise. And so the wavelength in the package that you're using, the mix of wavelength matters. We'll come back to that, but coherence has all to do with the mix of wavelength as well as with the angular size of the source there. And that's why we had this point source. We'll come back to that again. I'll just now go back to a cleaner way of representing that, where the holes are somewhat smaller. And here apparently, the way it's being drawn, we have only a single wavelength, and therefore you get a proper ripple there. The thing that is important to realize is that in fact you can reverse this picture and think of it in the other direction. You can see that light that comes from here, whereas it came from this way, we can also turn on a lamp here. And so in the hot spots, in the bright spots, then you would see the light coming out there. And if I would put my lamp there or there, the same would happen in the direction there. I would not even see the difference. So if I think of it not in terms of these fringes here, but I think of a receptor here, I make the waves just go the other way. I can think of having a sensitivity with respect to the center of this device, which is periodic on the sky. The sensitivity in the middle is high, and then it goes to 0, and then it comes up high again, and then it becomes to 0, and then it goes up to high again, and so on. And why is that? Well, that's for the very same reason as why we see fringes to begin with. That is because light that does come from there has one more wave this way and that way, and therefore they constructively interfere, and I can see it equally well. In fact, I can see so equally well that I can't see the difference. In fact, there is no difference. So the problem is, the real problem is that the light that gets emitted from the sky, from some sources in the sky, can constructively interfere if it sits in that band, or equally well in that band, or equally well in that band. And so, I hope you can understand that the bottom line of the story is that we have a banded sensitivity on the sky, which is a ripple with a period, which is one wavelength across the separation of the two receiving elements. And so if I bring these receiving elements close together, then the ripple is large. But if I put them very far apart, it's very many tiny little ripples next to one another. And so you can imagine that basically what we're looking at is at a weighted mean with this ripple as the weighting function, which is a very weird function you might think, but in fact I hope to convince you in the coming days that that is not so weird at all. But it's a weighted mean of all the sources out there, weighted with this ripply pattern. And so, in fact, a sensor at this location that's looking at the sky out there is looking at the sky with this weighted mean period, and that is what it sees. And if I put down these two slits sufficiently far apart, then the periodicity on the sky can be very, very high. Let's just take an example. I put two telescopes, say 100 kilometers apart, 100,000 meters. Then at 50 centimeter wavelength, that's 200,000 wavelength. That means that in one part in 200,000, 1/200,000th of a radian, you have the next ripple. And yet another, and yet another. And 1/200,000th of a radian, I hope you recognize straight away as an arcsecond. If you don't, we'll do the sum. In fact, that would be a good sum for you at home. It's one of these numbers that astronomers get so used to that they become natural for us. An arcsecond is 1/200,000th of a radian. So there's 5 arcseconds in a microradian. 5 microradians in an arcsecond, sorry. And that is the engineers use microradians. That's much nicer because you have radians or milliradians or you have microradians. But astronomers don't have that, and that is because accidentally the same arcsecond is 1 part in 200,000, which is the same as the ratio between our distance to the sun and our distance to the nearest star. The nearest star is sitting at 1 parsec roughly. That's why a parsec is such a handy number, a handy measure. That is the same factor 200,000. We find that in all sorts of other ways, also in optical telescopes. The atmosphere does not usually allow us to have any sharper images than 1 part in 200,000. So an image that is sharper than 1 arcsecond resolution is rare. Yet we want to see all these things which are much smaller than an arcsecond. And so we must have the receiving elements sufficiently far apart. Sufficiently far apart means much more than 200,000 lambda. And I hope to convince you of that as the driver of interferometry. Now, before that turns into an imaging facility so that I can just look at the sky with the resolution that I like, that is still a far distance. But it's good to realize that that is the basic trick that we want to try and achieve. So, then in fact that's what we're doing. We're looking at the sky and we're composing the sky with different ripples, even in different directions. And by having all these ripples in the different directions, you can basically in the end arrive at an image. But now I've almost told you how it all works. Let's try and see whether we understand it properly, and then we can soon have a quiz as to what you think would be the mathematical trick to make it all work. It's not so mathematical anyway. But so this is the sort of things that we want to start looking at. We want to understand first the single dish and demonstrate that the single dish is no more than an interferometer already. And then later on we will look at the basic interferometer and see the response to point source, see how that responds to an extended source. What we do in order to look at it that proper way, and then we have to evaluate our terminology a bit better, and develop the terminology a bit better, and then we can in the end demonstrate how that will come all the way to imaging. So again, it is because of the lambda over d, which is the limiting precision. That's good to see that if we want 1 arcsecond for 21 centimeters, we want to go already to 42 kilometer baseline. The telescope of 42 kilometers cannot be built, yet there are images available that astronomers have made with a resolution of better than 1 arcsecond at 20 centimeter wavelength. So they are sorcerers, or they have found a proper trick, and I'm telling you they have found a proper trick, and you're about to learn how that works. Let's look at a single dish first. The focus of a single dish, a big telescope, is in fact the location where rays that came from up there, but after impinging in this fixed dish, get to that focus by a reflection, and we know very nicely that you can reflect and devise the proper angles here, but in fact the shape of the mirror has been made in such a way that the path length from the source up there via the mirror to the focus is identical for all elementary elements in the dish. That is what this dish is doing. It's bringing this tiny little bit of light, or that tiny bit of light, or that one, all to this one focus at exactly the same time. And exactly the same time means within a small fraction of a wavelength. So I must make sure that the mirror is sufficiently precise to achieve that. I must also make sure that the atmosphere allows me to do that. And of course, if the source is then not sitting there but a bit to the one side, then it won't work, because then this path is too short and that path is too long. That's exactly what you can see here. If your wavefront is a bit tilted, and you tilt it by as much as a full lambda on one side, then for every element there's an element to be found in counterphase. So that gives extinction of the radiation, and so the source that would if I look at the source this far apart from the other source, then I don't have any light left. I drew that myself, but not so nicely, of course. So the single dish makes sure that all these waves arrive at the same time. And if you look slightly offside, then the fact that L1 and L2 are different is the cause for the fact that I lose response for this point source. Yet at the same time, if the source for which then these L1 and L2 are identical, then I get the light from that source. And that's the way we make images. But it's interesting to see what happens exactly in the focal point. You can demonstrate that in that focal point, the light gets together you can say that what happens is if I have two elements of this whole dish and gets together there as drawn with an L1 L2, then the field in the focus is then this, in this dish the integral of the field at location x cosine 2 pi nu t plus phi of x. This phi of x is interesting because I might have messed it up a bit with the form of the dish, but also the atmosphere might have done so. So basically the phase at each location of this incoming wave is not a priori completely constant, might be a position dependent phase to some extent, and we'll see later on that that is an issue. But for the time being, let's assume it's basically a single number across. That's the way in which we will get nice images. And that will be minus 2 pi L over lambda, because it went all the way back up there as well. So this distance we see as a retardation. So this is just the focal length. And that's stating that the field at the focus is retarded by the path length from the mirror before it gets there. But that's not a particularly interesting statement. but it happens.
What is E, the effective focus? You mentioned that E if, the quantity you are calculating.
That's the field.
This is the electric
field which arrived at the entrance at location X.
Okay.
Before it is on its way to the focus, which it will finally have arrived at, and that is that far later. So I've just taken a plane in the aperture and said I have the emerging and the imminent field coming in here. That field that is a field of E of X with an X all the way the aperture, and that on its way to the focus gets retarded by an L1 and L2 by an L in beginning. An L, which is an L, which is, you might say, of X, if it's incoming at an inclination. And that's exactly what I was going to say. So let's first be in focus. And then at angle alpha. Alpha. E F at alpha. From direction alpha is the same integral of E of X cosine 2 pi nu t plus phi of X minus this 2 pi L over lambda, but also minus 2 pi alpha X over lambda dx. And it's this term which generates the directional sensitivity. All the rest is just, yes, when it comes together it will constructively interfere. But this one specifies that I get a phase gradient across the aperture if I do not look at an on-axis source, but at the direction which is off-axis by an angle alpha. I still see people that don't quite believe me. I'm specifying an electric field that comes into my primary dish. That electric field is a function of location, and that gets reflected back up. And after L, it makes it to the focus. So at the focus, I'm co-adding this field. So I'm adding it. You see the addition sign here, that's an integral, just because I want to write it in tiny elements, but it is just an addition. I'm co-adding all these contributions of the field. And basically, all these different elements add up together, and they arrive there a bit late. That's all there is to it. But that's not so anymore if I go at an angle alpha, that I get a phase gradient across, and so I add, this might just happen to be pi. In which case, if this is pi, then one x and another x are counterphased. And so this addition is not particularly helpful. And that's that we are writing down here. We could have written that differently. We could have written it in a complex notation, and you will soon find out why I like that, I think, a little bit better. Also write that the field E of X is the real part of E of X e to the minus I, now the still plus I, 2 pi nu t minus phi x. And thus E in the focus equals the real part of the integral of E x e to the I 2 pi nu t minus phi x dx. But I should have put it here also minus 2 pi L over lambda dx. And that, again, is e to the I 2 pi nu t minus 2 pi L over lambda times the integral of E of x e to the minus I phi of x dx, because that's the only part that's dependent on x. Real of that thing. So E f of alpha is the real part of the same e to the I 2 pi nu t minus 2 pi L naught over lambda times the integral of E of x e to the minus I pi x plus 2 pi alpha x over lambda dx. And why is this interesting to put it like that? That is because, as you well know, e to the minus I 2 pi nu equals cosinus 2 pi nu minus I sin 2 pi nu.
Two things. First, I just want to make sure if I got things straight. We started saying that an interferometer is basically taking this configuration of the Young experiment, but putting it backwards.
Yeah.
Yeah. So that we get a fringe pattern, and if we put the little holes far enough apart, the fringe pattern is small enough for it to be useful.
Correct.
And what we're doing now is we're considering a parabolic dish, and we're calculating the electric field at the focus, considering
exactly. So what I'm saying is the imaging facility of a full dish that makes a nice picture of the whole sky, and once with a relatively nice resolution, but not good enough, as we will later see, is doing just what we're saying in elementary parts for an interferometer. Because I'm co-adding this thing and that thing, and if I had chosen other collecting elements, here, or here, or here, or further apart, if I had that still available, then they all co-add in the same way to the focus. And what I'm going to try and explain to you is that it doesn't matter if I do that all at the same time, or one bit today and next bit tomorrow.
So this parabolic dish is an interferometer, but you're just considering the little differential elements at opposing sides.
Exactly. And I want to demonstrate to you that a single dish is doing the same thing as interferometers do, a whole lot of interferometers. And then we're going to look at the details of a single interferometer, but we must also at the same time now understand how the single dish does make an image that way, because then we will from there understand how we will also be able to do it by having these single elements now and tomorrow and tomorrow and tomorrow and so forth. After a while have the whole set together that makes this image. I must understand that we are indeed observing something that we can stick together in a way which is very similar to what this single dish achieved for us to begin with. So the idea is that you understand that what an imaging piece of optics does is basically, if you look at it microscopically per square lambda or per little element in the aperture, then all these little elements can be considered as a pair of elements that together make an interferometer, and that gets co-added in the focus, and in the end that will become an image.
Okay. And another thing, can you please speak a little slower and a little louder?
Louder too? That's the easy part.
Okay.
The slower I'll try too. I shall try and speak a bit slower, but then you shall tell me when I get boring. Okay, I shall write bigger. Yeah, I get your point. I'm not known for my handwriting in any way. So it is disturbingly likely that sometimes you will say, what did you write there? And that it will try and help you. That is a flaw that I have never been able to cure.
So I have a little question there, because you take out of the integral in the second case, okay, in the normal case,
I take out everything that is just constant.
But in the previous equation, yes, you take out L, assuming that at any x, at every x, you will have the same length to the focus. But this will not be true.
Oh, I should have put it in here too. Yeah, you're right.
Right, but in the bottom equation.
Oh, sorry. No, this is not true, because
yes, of course,
this is just a field at
yes
the aperture.
But in the third equation, you take out the L from the equation, from the integral.
Yes, because I had a single dish which is so good that if I'm looking on axis, then all the L's are identical.
Okay, but this will be only true in the case of a sphere or something?
A paraboloid.
Oh, in a paraboloid, the distance is the same?
For a paraboloid it's the same, but in fact the wish for this length to be equal to this length, and to that length, that wish specifies the form of the reflector. And if you do your algebra properly, that will generate a paraboloid. But that is what an imaging piece of optics does. And in much of our optics, in regular light optics, where you make it with lenses, these lenses are still achieving the same thing. And that is difficult for these lenses to do that properly, and therefore you have lenses that correct for the error of the one and yet another one for the other errors. But in the end, the beam on its way to focus is as if it had traveled in such a way that all elementary contributions are coming at the same time in focus, at the same time defined to a small fraction of lambda. And it's that part that must work, otherwise it does not constructively interfere to make an image. the fact that it makes lots of light at the right spot and no light at another spot is because here all the waves help one another and here they counteract one another. That is what imaging does. And it's that part that you do not necessarily have to do simultaneously at one time, but you can do that as an elementary process for the combination of these different elements that are comparing one beam with the other beam, and from that comparison you get this ripple sensitivity on the sky, this sinusoidal sensitivity on the sky. And it's that part that we will bring together to make proper images. I hope you recognize here something rather weird. What you see here is an integral, an e of x, which is already with an e to the minus I phi. But the other term is the e to the 2 pi alpha x. And with a minus sign even. Minus I 2 pi alpha x. And this thing multiplied by that thing and then integrated over all x I hope you recognize as the Fourier transform of Ex e to the minus I phi. And this thing is just the complex field as it arrives in the aperture. So what we have seen is that the field in the focus and the Fourier transform of that field in the focus, the field in the focus and the field at the entrance are just related to one another as a Fourier transform. That is to say, that's not fair, I've taken the real part. But that real part only specifies that I was looking at the cosine. I can't look at the imaginary part. And if I do the same thing per element again, then you can see that one is the sine transform and the other is the cosine transform. The phi helps us understand that exactly. What happens is that if I think in terms of this comparison of this elementary element and that other elementary element, that's what we're doing here too in this integral, then I get this ripple pattern on the sky. And if I go back to this slide, this slide here, this ripple pattern, where my sensitivity is maximum if I look straight ahead, then if I would put in this hole a retarder of pi phase, then this maximum would shift a bit to one side. And I would be able to see flux that comes from where I can't see now. So what I would need is, I would need to look twice at the sky in order to get all the flux. One is with this sensitivity, and the other one with the sensitivity which is shifted 1/4 wave. So if I have a sensitivity on the sky which is like that, 0, 0, and here is maximum. And this is straight in front, in the middle between the two slits. Then I need to also look at the thing that is sensitive like this. To look at all these sources that are sitting at locations where the sensitivity was just very bad. In this one case, if I do this drawing very well, which I can't, then you will see that exactly at that location, 0, I get a maximum for this quarter shift. So I need, of the true sky, I need not only the cos transform, but I also need the sine transform. That's all what I'm saying. That's why what I need to do is I need to have a complex way of looking at the sky. I need not only look at the cosine transform, which would have with only 2 slits, but I will also 2 slits where one of the slits has a retardation of pi in. Now, that is not trivial to make a thing like that, but in reality it is. You'll see in very many cases, and so we are trying to observe this incoming radiation as a complex field where you look both at the sine and the cosine, or putting it differently, at an amplitude and a phase of the wavefront. And an amplitude and a phase of a wavefront you can understand quite well. You know, these waves are coming into us and we're collecting them with a single dish or with an interferometer or whatever. And the quality of the image is defined, for instance, by whether this wavefront around is sufficiently flat. The flatness of this wavefront is a crucial issue in all sorts of scientific applications. Distance of a source, for instance, has to do with the fact that it arrives here spherically. It's not flat, it is a sphere, because with the source in the middle. But stars are so awfully far apart that we consider these wavefronts to arrive here flat. And measuring distance is measuring the deviation from flatness. That's why distance is difficult in astronomy. Because that is exactly what we want to measure. But at the same time, that's also a point, if I got it corrugated, this wavefront, because of the fluctuations in the air density, I can't look any sufficiently sharp anymore. My picture gets a bit bad, and that is just because the wavefront is not flat. Yet, there's equal amount of flux coming in here as there is coming in there, but it's slightly retarded because the wavefront is a bit like that. So I can say that I have at this reference plane, which is a mathematically conceptual plane, I have incoming radiation that fits with this plane relatively well, but it is corrugated, and therefore the phase is a bit negative here and a bit positive there, and I have a phase that describes this function. And so that also describes how it can later on interfere. So I think in terms of electromagnetic waves as an amplitude and a phase rather than just a set of wiggles of which I hope after I put them together that I understand what's happening. And that's what I mean to specify with this phi here. But you see that this phi is not particularly interesting for the time being. This one is much more interesting, that's the directivity. And as long as I have long waves, and so what the atmosphere does is not so bad, and what my dishes do is not so bad, then I can understand all the geometry, and then phase is properly defined in this way. And only when the waves get very, very, very small, then I must think of all these other things that can corrupt all these phases, and then I have to do all the worries about that part. But it's good to think that we are thinking of complex waves that have amplitude and phase, so that they are sinusoidal, but they can be sinusoidal here or a bit shifted either way. And so that's what we're doing. And then the co-addition of that is indeed, and nature does that for us. So Fourier transforms are not math, they're physics. Nature does that for us. And so we are going to try and understand this part of nature a bit better, and we'll have to look more in detail into Fourier transforms. So that's what I intend to do first, go through the problem of Fourier transforms, which we will have to, otherwise we cannot understand the other tricks. And here you see the definition of a Fourier transform that says that if I make the integral of a function of x multiplied by e to the minus I 2 pi x times s, and I integrate over all x's, then I get a number for a given s. That given s that specifies the ripple that sits in function x. So basically this f of s is a measure of the ripple for every period. This s is a separate period. If s is getting very small, then the period is very long, and if s is very large, then the period is very fast. So yeah, it's basically decomposing a given function, f of x, into all its harmonic constituents. And now you see straight away that here mathematically, of course, I have something written down of which we must discuss the existence. It's not necessarily good that you can integrate from minus infinity to plus infinity, and there's all sorts of troubles of that nature in this definition. But we're talking about a real function, a physical function of x that began at some time and it will end at some time, well before infinity, and it started well before negative infinity, well beyond negative infinity. So these infinite integrals are not particularly interesting in that respect. And I can look at such a function in terms of the harmonic components in there. In fact, that is what we're exactly doing if we look at an image, because, as we said, we have a ripple pattern on the sky in sensitivity. And the faster we can make these ripples, the finer we can locate the source that generated the pattern that I can see on my sensor. And the slower this period, the more I can add together all the flux from sources together, or of an extended source or something like that. So what I'm doing is I'm trying to, in the long run, understand the spatial frequency content of the source out there, which is making the image in the end. So a Fourier transform basically looks at the frequency content of the function x. And s is the frequency and x is the spatial coordinate. But it can also be done in the time direction. So if I put x as time, then s of course is 1 over time, which is frequency. And therefore, if x is length, then s is 1 over length. That's the number of periods per unit length. So s is then the number of periods per unity of x. And so that's the way of looking at this thing. And we see straight away that we will now get troubles, because we can, for an even function, which is a function which is identical on either side of the origin, we can demonstrate that we can go back at the function f of s, which specifies the frequency content of f of x. That can be Fourier transformed back, and then I get back all the way to f of x again. However, for an odd function, where f of x is the negative of f of minus x, then I find myself with f of minus x instead of f of x. That's not handy. But it is not particularly amazing, because what I have done is I have multiplied by I squared in going back and forth. So what I'm specifying is that I squared is being -1 is the very source of the whole trouble. Or putting it differently, if we specify it separately and we don't like real and imaginary parts, but we talk about the sine transform and the cos transform, then you can show straight away that the sine transform specifies everything about the odd components, harmonic components of the function, and the cos transform specifies everything about the even component. So the very fact that this holds, which says that I can also take the cos transform and in some other coordinate, which is the I coordinate. In the I coordinate I can take the sine transform. That's only saying I take two different things and I put them in a different coordinate system. And nicely orthogonal to one another, which is very handy because then I can see there's a rotation. But in fact I'm saying that a sine transform does the odd part and a cosine transform does the even part of the frequency content of this function f of x. So odd and evenness is a very important part of the story. And so the symmetry is not perfect, but for the same reason, because oddness and evenness matters, you can also see the location of the origin matters. If I shift f of x to another location, I look at fx minus a, then the oddness and evenness in the function changes. And so obviously the f of s must change, because then these statements still hold. But then they hold with the f minus a and so on. So as long as we make absolutely sure that you swap the sign on the way back, so you make sure that you undo the I squared equals -1, that's basically what we're done doing, then you have a statement that always holds. But then you have made a difference between going one way and the other. And that of course for a specific problem is not that bad. You might consider going from x to s being the natural way, but it's not always true, of course. It is sometimes much more interesting to go from s to x. And if you have a f of x of which you want to find the f of s, then you call that the Fourier transform. And then this definition would not hold properly for the Fourier transform, because we have defined it with the minus sign.
This is only for odd functions.
This problem is, no, this is now for an arbitrary function. Because I've made a plus I sign transform. So I've taken away the issue of the I squared -1. Better is to remember this, the oddness and the evenness. Because in fact, that is a relevant parameter in what you're trying to describe, you will see very often. So the fact that some functions have odd and even components is not accidental, but it actually holds information that you want to know. I'll show you examples where indeed the oddness is the part that you can't find, and that's the one that you did want to find because it specifies the phase of where the signal comes from. I can only get symmetrical images around a central point if I look at even functions. An odd function is not in there, and therefore I cannot specify flux that is different on one side from that position, from that on the other side. So I can only construct images which are circularly symmetrical with even functions. That's not good. And so oddness is important. And that is all about location of the origin, because this object is sitting there. But oddness and evenness is a serious component of the whole story, and that's why it's important to realize that this may look as a nuisance, but this is in fact exactly what you want. It's doing it. It retains the information in the process of Fourier transforming, instead of washing it away. And this washes it away. And putting it differently, as I already said a few times before, you want an even transform, but you want to specify also the frequency content of the odd part of the functions. And therefore, you want to also look at the odd transform, which is the sine transform. And that's very interesting. You know straight away that from now on, in a Fourier transform, the even part of the story is in the real part of the Fourier transform, and the imaginary part of the Fourier transform holds the oddness. So the Fourier transform of a function is a function which is partially odd and partially even. And the partially odd sits in the imaginary part, and the partially even sits in the real part. So if I have a function which is only even, and I make a Fourier transform of it, then the imaginary part of the Fourier transform is 0.
Again.
Right. If I have a function to be Fourier transformed, which is intrinsically even, for which holds that f minus x equals f plus x. So if I draw that function graphically, then I can fold it around the x equals 0 line. That's an even function. It can be as weird as you like on either side, but if I fold it, it fits. That's what an even function is. And insofar as it does not fit, there's something different from that side and that side. And that part is odd, because what is different there from there must be described with the difference between f minus x and f plus x. So an even function is a function that you can fold around the y-axis of a graph, and it fits. And anything that does not fit, if you do that, is the odd part of that same function. Might be because you didn't draw it well. That doesn't matter. If you draw it precisely well, it would fit. And if you have drawn it so that it doesn't fit, then you have drawn partly an uneven function. So if you try to draw an even function and it doesn't fit, then you failed, because there's some oddness in there too. It's good to realize this oddness and evenness. I'll come back to that quite a bit in the coming hour or so, because it is such an important parameter. And of course it specifies, if I want to specify flux in that area of sky, it specifies where, with respect to some origin, that flux resides. And so the odd part of the story is an important component of the whole story. Otherwise you cannot relocate things, because the only thing that you can see is a symmetrical function, symmetrical around the origin. That's all that you have in an even function. So again, but now in pictures, I have a real function. Does this thing also? Super. I have a real function which has no imaginary component, and by the way, it happens to be even, and therefore it doesn't have an imaginary part here. Well, that's not so. It could have an imaginary part, but the real part is even. Then in the Fourier transform is still even. I have a real part where f minus x equals minus fx, which is fully odd. If a Fourier transform that, it sits completely in the imaginary part. So the Fourier transform of a odd real function is completely imaginary. I could have an arbitrary function f of x which happens to be completely imaginary. If I Fourier transform that, if it is even, then it will transform into fully even. But it will still be imaginary. If I have imaginary odd, so I have a completely imaginary function with no real components, but the function is odd, then the Fourier transform will be completely real but odd.
So,
Yeah.
since an image produced by a dish is the Fourier transform of the field,
Yeah?
if the field is odd, we will not have any image, because the image is the real part of the transform. I'm wrong.
This realness, I'll come back to that soon, we'll see that, but we'll have to look at the Fourier transform of a real arbitrary function, a function that's completely real, because the intensity distribution out there is real, and I'll show you that we are observing the Fourier transform of that intensity distribution. In there, the evenness and oddness is only about the location of the origin. If I have an arbitrary function, I move the origin in that arbitrary function, then I move components from the real to the, from the even to the odd part, and the other way around. Sorry. Go ahead. So the location of the origin, and that is in terms of looking at the brightness of the sky, is just the definition with respect to which I want to describe this intensity distribution. That could be with respect to the center of the viewing direction of the telescope, for instance. If that is the origin and it sits a bit on one side, then it is odd because it sits there and not there. And so the symmetry is not around the origin, and therefore it is odd. And then it transforms into imaginary. But you'll see that a real function has a very special, I'll make that statement straight away here. A real function, completely arbitrary but completely real, has a totally real even part of the Fourier transform and a totally odd part of the imaginary part of the Fourier transform. So I know of the transform of this arbitrary real function, completely arbitrary, a property which specifies that the real part of that function is even in the Fourier transform, and the odd part of the function is imaginary. So the Fourier transform of this totally arbitrary function here, sorry, he doesn't like me. I'm asking him to go back. There we are. A sort of arbitrary real function is, for its even part, transformed into a real story, and for its odd part, in the uneven part, in the imaginary part. But Hermitian, that's not a standard function. That is a function that comes about if I transform an arbitrary real function. It specifies basically that I don't need to look at negative frequencies, because at negative frequencies I see the opposite of what I see at positive frequencies. So a Fourier transform of a real arbitrary function is fully specified by only half of the Fourier transform. because I know if I have this part available, I know the other part, because the other part is for the real part the same, it's just mirror image, and for the odd part is mirror image flip. So I need, in the case of a Fourier transform of a real function, I need not have the whole Fourier transform, half of the Fourier transform is enough. And that's very handy, that's a very practical property, but if you look at it later, we will exploit this, because if we do later on Fourier transforms in two different directions, because we do a Fourier transform for these ripples, but also for those ripples, so we have all these different elements sitting in different directions, and we make a Fourier transform in two directions, then you can see that you do not need to observe the elements around. The opposite does not give you anything new, because I'm observing the same Fourier transform, but it's the Fourier transform of a real function, and therefore it's Hermitian. And I know already from having observed this, what I will observe, I will observe it like that. So apparently I have the right description. You're not convinced? Is it clear like this? So I said already there is a potential problem here that we have not properly defined where Fourier transform could possibly exist, because I'm integrating from minus infinity to plus infinity. And it is not particularly demanding what we request here. And as I said, we were looking at proper physical functions, and so it's disturbingly unlikely that we make troubles there, that we encounter troubles there. However, the Fourier transform of a straight function, that's unity all over the place. That's a problem. Because I cannot integrate f of x. So this doesn't hold. The same problem here. Or, for that matter, this is a rather weirdo function, because fx of 0 is infinite. And we had agreed that we wouldn't do that sort of things. But we have defined a delta function in such a way that the integral from minus infinity over the area of x0, and we may take any arbitrary small integral area around it, yields unity. That's the way we define delta functions. I am not sure whether you have already encountered delta functions in other classes of physics or so, but this is a rather weirdo function, but it's only a mathematical trick. But it is a way of specifying that I want only this value of a function. A delta function times a function gives me value, it allows me to put that function in there with a proper weighting. So these are handy tricks that we have all devised that are in fact, for the description for which we want to use them, are non-existent. There isn't such a thing as a field that has such a intensity for a single value of nu, because that single value of nu requires that the field was turned on infinitely long ago, well before the universe started, and will outlast the universe for a long time. That's the only way in which we can properly specify a function which is cosinusoidal for a single frequency. So we're talking about non-existent functions here, which are handy as approximations, and we must make sure that these approximations will not hurt. That's basically what we're saying. And there's tricks around that. Let's just look at a few Fourier transforms. A very nice one is a Gaussian. The Fourier transform of a Gaussian is a Gaussian again that says that if I have a very narrow Gaussian, and the Fourier transform of that is very wide because it has very high frequencies in there. I have a very shallow Gaussian, and the Fourier transform of that is very narrow because I have only very slow frequencies in there. And the frequency content of that function of a Gaussian is specified, and is weirdly enough, the content is a Gaussian. It's not naturally trivial that that should be so, but that's something that can be proven if you try and do statistics very properly with the central limit theorem. In statistics, you can demonstrate that this is what comes out. But it's much too evolved to go and prove that, but it's handy to remember that Gaussians are their own Fourier transforms. Well, not completely their own, because the wide one gets small and reverse, because in one way the x's are size in physical space, and the s's in that sense are the size in how many times per unit length in the other domain. So it's spatial frequency or temporal frequency. If x is time, then the s is, of course, a frequency. But that's the nice thing of it. The direction of x and s are opposite. So one grows, and therefore the other ones get smaller. Another one that's a weirdo one. I have a function which is unity. We have already agreed that unity is troublemaker. You can't properly define a Fourier transform. But if it is only unity over a fixed part, then of course it's integrable. And so that should yield the proper Fourier transform. And indeed it does. It is a very, it's a very peculiar function. It's the sinc function, which is sinus x over x, and then scaled with the pi in there in order to make sure that the normalizations fit properly. So this is a function that's defined and grows linearly with distance from the origin, grows smaller and smaller and smaller, but it remains periodic, sinusoidally periodic. It's the ideal interpolation function on a rectangular grid. The sinus x over x, sinus x over pi x is 0 at 1, 2, 3, 4, 5, and only non-zero, unity, at 0. So if I'm ideally interpolating, then I get only the function back at the location of that origin. So if I have a set of numbers at such locations, this, that, and I want, these are just samples of a function which is continuous, and I want a number in between here. The best way of getting this function is to take sinus x over x as the weighting function. So you get alternating contributions from these functions, and you get exactly as if you had observed it at this position. If you go long enough, because I make errors which go with 1 over the distance. It dies out relatively slowly. So computationally it's an unpleasant function because it remains very long, significant. A Gaussian is much nicer. If I want to look at only this part, and I take therefore the function times the Gaussian, that function is absolutely dead a few Gaussians further away. That's not so for sinc. So these two make a Fourier transform pair. And in the same fashion, we have a function which is this block function, but then wider and sloping. It is from 1 to 0 on either side of 0, that has a Fourier transform which is this sinc squared. So it now becomes positive definitive. It has no negative components anymore. I can, starting from expression here, I can demonstrate how a Fourier transform scales. If I take x to go as with another scale, a times x, and I make a Fourier transform of that, then I get out y over 2a, and I've put y now as ax, and then I can make the new integral, and I get a to the minus 1, so 1 over a, and the scaling changes by the same a. So if I have, instead of a unit at this distance, I have a unit at this distance in x, then for the same reason, the Fourier transform scales the other way. And in order to keep the normalization proper, I've got to put this a to the minus 1 in there. You can specify that thing more symmetrically. If I take an a x there, then if I take a absolute to 1/2, and I have an a and a b related like this, then b to the 1/2, again absolute, times bs is the Fourier transform. So now I can scale Fourier transforms completely and go from one domain to the other. In fact, and that's good to realize, I have now found the trick out from our problem here. We had a problem here. If I take fx as unity, that I can't Fourier transform because that thing doesn't exist, that integral doesn't exist. But fx times a Gaussian, which is kilometers wide. In my book is very narrow and it's very precisely f equals 1, right? Yet I can Fourier transform it then, if I take it times that Fourier. And then out comes a function which is also a Gaussian. And as this thing is so awfully large, the Fourier transform is awfully small. And obviously it's awfully small and therefore very tall, because the integral must be 1. And so I'm getting pretty close to this function here. And you may bet, of course, that you will find that the fact that I'm talking about of this one and of that one together has to do with the fact that they are basically a Fourier transform pair, although they're both not defined. But it says that an ideal pulse, because that's what the delta function is, it's a frequency in there. Every one, infinitely high even. That's not physical because you can pulse whatever you like, but you can't pulse infinitely fast. There's time involved in making a pulse. But an ideal pulse, and an ideal pulse is faster than all your measuring equipment. That's an ideal pulse. That ideal pulse has equal content of amplitude in the signal at frequencies. And that is also not lasting forever, but lasting in this kilometer-long Gaussian. So it fits still. So you can prove these troublemakers as Fourier transform pairs by modifying the function slightly, but irrelevantly, by having a very large or a very narrow Gaussian on there. And I can do the same thing, not necessarily by means of this Gaussian, but I can also do it with the sinc. I can make this sinc awfully wide, and then it is unity forever. Very late it gets small. And in return, I get a block function which gets extremely narrow and very tall. So I can use either one of them to get myself out of these troublemakers. We had already put the similarity theorem in there. So it says that time dilatation and frequency compression are equivalent concepts, and a larger aperture causes a narrower beam. That's also the same story. And so we have not changed the picture, but we have only changed the scales. That's in both cases the fact. And it's interesting to know that if I change the scale in one domain this way, then in the other domain necessarily it goes the other way and it gets smaller. So now we have the problem straight away. What if you go with a to 0 in the limit? Well, then indeed we find that we're basically talking about f that tends to unity. And on the other side we find something that tends to the delta function. So it's exactly what, as we said before. There you can see the examples. A Gaussian transforms into itself. A block function has too much frequency here, but not enough further than that Gaussian, so it looks in the central part somewhat like a Gaussian, but it deviates rather dramatically from a Gaussian further out. This is the way to make sure that the Fourier transform does not go negative, which is also weird. So just by sloping this, I get rid of these negative sides in the Fourier transform. We will find a way of proving that very easily. And we'll come to that a bit later. I don't think this hour, but just after 4 later on. You see here the Fourier transforms that don't exist and those are still each other's Fourier transform pair. And interesting to see also that a cosine can only be described with 2 delta functions. And if I shift that, it becomes a sine, and it's also 2 delta functions, and this function is purely odd, and therefore Fourier transform must be purely imaginary. And if I have 2 delta functions, purely odd but real, then I get an imaginary sign. Again, it's only to make you extremely sensitive and aware of this issue of oddness and evenness of functions, so that you know which part of a function ends where in the Fourier transform domain and back. In the long run, that's what you will have to try and learn. You'll see that later in the images that one can produce. You can and must think back and forth across the Fourier transform and see, oh, this defect, that must be that baseline that did this thing for me. And so error searching in a process where I have the Fourier transform as a hard component in there requires that you can think back and forth across the Fourier transform a lot. And that's why I think it's such an important thing. At the same time, it's also very interesting to recognize time and again that I'm not doing math here, I'm doing physics here. I'm trying to describe what happens on either side. Okay. In the ideal case, fx and fs are entirely equivalent descriptions of one thing. You can either describe it, if I go so far that way, so much happens with my function, or you can also state, if I take that much more frequency in my description, I get so much more. And the only problem occurs when we do weirdo things, where we ask for a sinusoid, which lasts infinitely long and so on. And so we've already demonstrated that multiplying by a Gaussian of sufficient size helps you out and makes things existent again if they did not exist before. So, these are still the known troublemakers. A delta function, also a step function, which steps at the origin, so it's 0 up to the origin and it goes bang up to 1 and it goes on at 1. That's a thing that is of course not necessarily easily Fourier transformable. But even if things don't exist precisely, then that's not the fault of physics, this is our fault, because you don't mean it if you want to describe something by means of a proper harmonic function. That is no physics, because you are not describing something that was already turned on before the universe started. So it's our own fault that we get troubles there, and we have then used this harmonic function as an approximation of what we're trying to describe. And we must not be so dumb to not notice that. And it's very easy because you can repair it by having it start somewhere after the Big Bang and die in another billion years or so. That means that there is not zero bandwidth in there, but there is a slight mix of frequencies involved. That's all there is to it. Now, if that slight mix of frequencies is so narrow that I don't see the difference between a single frequency or that mix, then I say it's a single frequency. But mathematically, I might be in for trouble if I want to rely on the fact that it's only a single frequency. But nature knows the difference. So it states yet another time that you can repair the weirdo cases. I think we should stop here, and then at 4 I hope to complete this at least to a nicer point to make a proper of it. I don't think we can complete the whole of the description of Fourier transforms today, but so that will be tomorrow morning. I suppose that we finish that at the end of the morning. But then we stop here for 1 hour and see you at 4 again. But I don't think you ask very many questions. So try and think of something.